Alright, so let's continue from last time. So we defined the notion of height for algebraic numbers. And then we wrote down the following lemma. So take P of t. A polynomial with integer coefficients, which is irreducible. All the coefficients are relatively prime. So if irreducible in the rings, the adjoint T. And P of alpha is 0. And you can measure the height of alpha just by looking at the coefficients of P. So you can write the height of alpha 1, let's say, let me change it a bit, So let's say alpha 1 through alpha d are the roots of P. So then get all conjugates, so the height's all the same. And the height of alpha 1 times d equals the following thing. Plus the sum over j of log plus of this absolute value. Whenever I just write absolute value, I mean the usual Archimedean absolute value. Usually sort of inside the reals, inside the complex numbers. Okay? Alright. So, let's prove this. So we're going to start by taking K to be a number field. So a finite extension of Q containing all the alpha I, so all the alpha j, 1 through alpha d, which is also gal I. Okay. Now we can write P of t as the leading coefficients times the product of t minus the roots. And so now recall what Gauss's lemma says. It says if you write P of t as two polynomials Q of t times R of t, then you can read off the valuation of P of t from the valuations of both of these guys. Right? So normally what it says is that if the coefficients of Q are at least one coefficient is not divisible by P, and at least one coefficient not divisible by P here, then at least one coefficient here is not divisible by P. But what you can really use it to say is that for any non-Archimedean place V, you have the following equality, where P of t, the norm of a polynomial, this is defined as the max over all its coefficients. Okay? So this is Gauss's lemma, and the proof is really quite, I mean, you can think about it just for V finite. For any finite place V. So if you want to just think about integer coefficients and V being a prime, sort of the same, and that's the case essentially we're using anyways. So then the point is you can just multiply both sides till this norm is 1, and that means that both coefficients, all the coefficients are algebraic integers, and you have a coefficient here and here not divisible by V. The reduction must be non-zero, which means the product is non-zero. Okay? Okay, so I'm not going to say more about it, but you can sort of look it up. It's well documented.
So you need those polynomials to be like rational, or what?
You need these polynomials to be.
I'm just thinking about the case where you write a cyclotomic polynomial. Or,
Yeah.
Sorry, you factor z to the n minus 1, and then one of the cyclotomic factors can have non-unit coefficients. But the product just has 1 as its coefficient.
Sorry, I'm not sure I understand. So you're saying if you write like.
Yeah, t to the n minus 1 into
Yeah?
two things, one of the factors is going to have a coefficient which is bigger than 1.
You mean this?
Not those two factors.
Oh, not those two factors. Two other factors.
Yeah.
What can I do with t cubed minus 1, which is the fourth minus
No,
1?
you need cyclotomic polynomials. Like, one will have a cyclotomic factor where the coefficients aren't just 1 and minus 1.
Yeah, but why is that a problem?
But then it's going to have a prime factor, whereas the left-hand side has no prime factor.
But remember that what this does is if you're divisible by p, then your norm is 1 over p.
Right, okay.
And so this gets bigger the less divisible you are by the prime, not the more divisible you are. So the key is they both have at least one coefficient, which is not divisible by the prime.
Right, okay.
Mm-hmm. Yeah, no, that's important. Thanks for making that mistake, because I make it very frequently. It's an important mistake to make a few times, so you're aware of it. Okay, so let's use this. If we apply Gauss's lemma over here, then we learn for any finite prime, what we get is that if you take the norm of AD and you multiply by the norm of this polynomial, of all these polynomials you get 1. And so what's the norm here? Well, it's exactly sort of the product j from 1 to d of the max of 0, which is the norm of this coefficient, which is 1, and the norm of alpha j. So what you learn is this product is equal to 1 for all finite places. Okay? So taking logs, we can rewrite that as the log of this plus the sum of all these log pluses. It's nice to have these guys appearing because we want these guys, is equal to 0 for all finite v.
So it's not maximum.
Of 1 and speed.
Sorry. The maximum of 1 is the product, right? I was taking the log in my head. Thanks. So you learn this, and so we can write this guy. Sorry, just log of AD now is minus of these guys. This is by the product formula. And now for each finite place, sorry, sum over v. Sorry. Yeah, v doesn't divide infinity by the product formula. And then we write this as a sum over v doesn't divide infinity of these guys. Okay. And this is almost the height of alpha j, it's just missing the Archimedean places. Right? So now switching the order of summation, what we get is the height of alpha j, because we have the sum over all finite places. Now we have to subtract the Archimedean places. Right? So now this guy over here is just dH of alpha 1, because all of these guys are algebraic conjugates, so they all have the same height. And this guy over here, well, you're taking the norm with all these various embeddings, but this is already a complete set of conjugates. So the only numbers you're seeing here are the absolute values of the alpha j's themselves. And so this is just the sum. If you keep track of the normalization, which I'm not going to do carefully, this is exactly this. Okay. And so rearranging, this is the formula we had at the beginning. Okay. So it's a bit of voodoo to actually sort of set it up correctly. But in terms of the statement itself, it sort of makes sense. What it's saying is that if you look at the height of an algebraic number, what you're doing, you're sort of summing up how big it is in an Archimedean sense, and then you have a sum over all these finite primes. And what this lemma is saying is that sort of the amount that your guys know an algebraic integer is precisely measured by the leading coefficient of its minimal polynomial. Okay, that's sort of, yes?
Why is that product 1 again? I don't quite.
Why is this product 1 again?
Yeah.
So by this lemma, so because of this result here, the norm of the v-adic norm of P of t is this product.
Right.
And the coefficients of this are relatively prime integers, which means that its norm is 1 for any finite place. Okay? Yes?
In principle, the statement of this lemma can be taken as a logarithmic definition, as a definition of logarithmic pi.
Yes, that's right.
Because minimal polynomial is unique, algebraic number, so
Absolutely.
and if you exponentiate, we get absolute
Absolutely.
pi. So
That's right. Yeah. It's a little harder to prove some of the basic properties, but you can still do everything if you want to do it that way. Totally. Other questions? All right. So we're getting close to proving, having enough machinery to prove Bilu's theorem. You just need one more idea, which I'll do right now, which is the discriminant of a polynomial. So if you have a P of t is, let me just write it like this, some polynomial leading coefficient is AD and whose roots are the alpha j's. We have a notion of the discriminant of P of t, discriminant of P, which is defined in the following way. It's AD to the 2D minus 2 times the product of all these guys squared. Okay. Now by Galois theory, you can see this guy is actually a rational number, because if you apply a conjugate, it sort of permutes these guys. So up to a sign you're fine, but you have the square, the sign goes away as well. In fact, it turns out it's actually an integer if you throw in this normalization. That's not trivial to see, but another way to see it is this is the resultant of P and P prime. You can think of it somehow this way. And what does this mean? Well, this means you take the following giant matrix, you take the coefficients of P of t, you write them in a row like this, you shift them a bunch, then you write the coefficients of P prime, D, AD, A1, you write them in a row, you shift them a bunch, you end up with a, let me make sure I get this right. I think it's just a 2D by 2D matrix. Arun, is that wrong? Okay. You get a 2D by 2D matrix, and you take its determinant. So the determinant of this guy. All right. So what's happening here exactly? So whenever we write two different polynomials, f and g, you can write the resultant, which literally means do this. So once the determinant is 0, it's exactly 0 when you take a linear combination of the rows and you get 0, which means you have some polynomial relation between these guys, which is small degree. And it exactly means they share a common root. And when this p and p prime share a common root, precisely when two of the roots agree. Okay? So because of that, you can see that this and this are the same up to sort of a constant, then homogeneity concerns give you that. 2D minus 2, yeah, I was getting that in my head as well. Okay. Thank you. 2D minus 2 by 2D minus 2 matrix. Okay. All right. Questions about this? We're not going to use resultants very much at all or ever again in this course. So you can just take for granted that dp is an integer, or it's also a fun Galois theory exercise to prove yourself. Another way to think of dp is if your leading coefficient a sub d is 1, then this is the discriminant of the ring, which is z adjoint any one of these guys. So z adjoint t mod p of t. That gives you a ring. Its discriminant is p sub p. All right, so we're going to use that it's an integer. And sort of one thing it says is that this number, if it's not 0, has to be at least 1. Right? So it's sort of, we're going to use it in part as a statement of saying that no two of the roots can really be all that close. Because if two of the roots are too close, then this number gets very small. All right. So I think that's all the setup we need. Now let's start the proof of this theorem of Galois. This is a very important theorem. It's led, and it's still, I think, leading now to sort of many important generalizations. And it's sort of a new approach to a lot of these questions in equidistribution and number theory. So suppose you have a sequence of algebraic numbers in alpha I, in Q bar. These are distinct numbers. And suppose that the height of alpha I goes to 0. So one example is roots of unity, but of course there's sort of lots of other examples. So now set mu I as the average measure over the Galois conjugates of one of these guys. Just like before, we look at the Galois orbit, and we take the point measure, and we average that. That gives us a measure. Then mu I converges. As always, for us, convergence of measures always means in the weak star topology to the Haar measure on S1. Okay. So any sequence of algebraic numbers with height going to 0, look at your Galois orbits, sort of distributed uniformly close to the circle. This doesn't actually mean, note, that any of the Galois conjugates lies on the circle, right? Because it sort of gets closer and closer. All right. Okay, so sort of many things aren't obvious. One that it sort of converges at all, and the other that it lies in a circle. So we'll start by proving that whatever the sequence converges to something on the circle. So here we don't have to set it up this way, but it's very useful to in practice. So because the unit ball in terms of measures is weak star compact, as we talked about last time, we can always pick a subsequence which converges to some measure. Okay? So by taking a subsequence, we can assume that the mu I converges to mu for some measure mu on, I don't know, C star, for example. Okay? This measure might not be a probability measure, a priori, and it might actually be zero, for all we know. If your points go further out and further out to infinity, and the measure is actually zero. This is the phenomenon which sometimes happens, and it's very important. But we can assume it sort of converges somewhere. Okay, so now that's sort of nice, because now we can sort of ask about properties of mu. We know we have a limit to begin with. Makes the problem easier to tackle. All right, so first let's prove that it sort of doesn't go to infinity. It actually stays near the unit circle. That's substantially easier to show. So claim mu is a probability measure. Supported on S1. Proof. All right, so fix some epsilon bigger than 0, and we're going to show that the measure is supported on the disk of radius 1 plus epsilon, every epsilon. So what's our sort of methodology for showing it doesn't get too big? Well, all we have are these height bounds. So we know that the height goes to 0. We also know that the height is sort of a sum over all places of this log plus thing. So in particular, it's bigger than or equal to, let me call d sub I the degree of alpha I, for convenience. So we know the height is bigger than or equal to the average of the log plus of all the absolute values of which conjugates. So it's bigger than or equal to 1 over d sub I. I'll just write sum over all sigma log plus of sigma alpha I. Okay, it's actually equal to this sum plus a whole bunch of other things coming from the finite places, and that all goes to 0. All the terms are positive, so at the very least, this sort of goes to 0. Okay, and this goes to 0, all the terms are positive. Therefore, the sort of percentage of sigma such that sigma alpha I, its norm, is less than 1 plus epsilon divided by the number of all Galois conjugates, and then divided by d sub I, goes to 1, as I goes to infinity. Otherwise, this limit would be at least epsilon. If you had, it goes to 1. If you had a positive proportion of conjugates which had norm bigger than 1 plus epsilon, this average would be at least that constant times log 1 plus epsilon, which would not go to 0. Okay? Because this guy tends to 0. Okay? So you sort of, the picture is here you have the unit circle, this is radius 1. Here you have a slightly bigger circle of radius 1 plus epsilon, and you know that eventually 100% of the points lie in this ball. Okay? And this ball is compact. So therefore we can conclude that whatever the measure mu, you can think of it as a probability measure on this sort of closed disk, on the set Z with normally multiplying. It's 100% of the points eventually lying there. Questions about this? If you want to see it formally from the definition of measures in terms of compactly supported functions, you look at the compactly supported function, which is 1 here, and then sort of dies out to 0, and its integral converges to 1, which means your measure has to be a probability measure supported on here. All right. Okay, now we sort of see that it's also supported on the outside of this. So we note that the height of 1 over alpha I is equal to the height of alpha I. Recall that. And so therefore, by the same sort of logic as here, the number of sigma such that sigma 1 over alpha I is 1 plus epsilon also tends to 1. That goes to infinity, because by the same result to sequence 1 over alpha I, which means the percentage of conjugates which are greater than 1 minus epsilon also tends to 1. But eventually, if you look at any sort of annulus around this one, 100% of the points will lie in this region. Okay? And so from this, you get that mu is supported on the set of Z with norm at least 1, and the intersection of these two sets is exactly the unit circle. Okay? Questions about this? The legality of this? Later on, we'll be sort of at least for some amount of time, we'll be talking about this theorem for elliptic curves, where it will be a little easier at this step because elliptic curves are actually compact, and so you don't have to worry about escape of mass or things like this. This is sort of an extra bit of concern because C star is not compact, and we're sort of interested in the compact piece of it. Okay. Okay, so that was pretty easy. Sort of get the measure on S1. So the next part is surprisingly difficult. I mean, it's not difficult to give the proof. It's sort of difficult to come up with it. So it's somehow the natural thing to do, in some sense. The thing with it for retrievability is to take sort of test functions. For example, the characters are very natural sort of test functions, and show that the partial sums become what they should, sort of that they go to 0 or infinity. The problem is you can't do that because it's not really true. So your enemy is the following. You could have a situation where you have like, this is all heuristic, what I'm writing here. You could have a situation where you have alpha 1 through alpha d minus 1 very, very close to 1. And alpha d, for example, is approximately d squared. And say everything is an algebraic integer. So suppose you have a situation like this. Then first of all, the trace of these guys is roughly d squared. If you sum them all, you get something roughly d squared. There's no way the partial sums become what you want them to become. At the same time, the height sort of does go to 0, because these guys, you're summing logs, right? So log of this is 0, log of this is log d, And if you sum that and divide by d, you get like log d over d, and that goes to 0. And so you can very well have a sequence of algebraic numbers that have sort of one outlier, one very big conjugate, but at the same time, it sort of doesn't contribute enough to the height to throw you off. And so it's not just you can't sort of prove things with this partial test function. It's not even true. On the other, yes?
Okay. Maybe this is the wrong way of thinking about it.
What?
But since you have the theorem is supposed to hold for an arbitrary sequence.
With height going to 0, yes.
So you could twist your sequence by roots of unity. And
Yes.
shouldn't that tell you that whatever measure you're going to converge to has to be rotationally invariant? Something like that?
Oh, that's a clever trick. No, I don't think so. Because to get a measure a priori, you got to take a subsequence. And your subsequence is not going to use your sequence of twists.
Okay.
Right? If that worked, then you wouldn't need the height going to 0 assumption. If you think about it.
Okay.
Yeah. No, it's a clever trick though. Things like that will eventually work. But not in this generality. Somehow you have to assume you have some twist action to begin with. Yeah. At the same time, note this one outlier, while it throws a trace off, doesn't actually affect the limiting measure very much, because it's just one point. So the limiting measure of this sequence, of this set of points, is the same as if you remove any one point. That's the same if you remove any number of points with sort of fraction going to 0. So, anyways, I just wanted to bring attention to this sort of enemy, and this is the reason why we can't use this test function argument. Instead, we're going to use a potential theory argument. Okay? So instead, what we're going to do is we're going to study the energy integral I of mu, which is the integral of log norm x minus y d mu x d mu y. Okay? So why this function, you sort of might ask, what's the point of running this function? Where did it come from? Well, it exactly came from the notion of a discriminant. The discriminant tells you if you multiply alpha I minus alpha j over all pairs, you sort of get something that you can understand. And that's exactly, if you take log of that, summing log of x minus y over all pairs. So that's where the motivation to study this guy came from. And so we're going to show the limiting measure gives this the largest possible value it can attain that uniquely determines mu. So it's a very sort of strange sort of argument, but it proves very, very powerful, and it has many different generalizations. All right, so let's actually do this. But as far as I know, no one knows how to prove the spectrum distribution theorem using integration of a series of test functions. So I haven't seen an argument like that work, and I would find it very interesting at least. All right, so let's start with a preliminary claim. So mu assigns any point, any one point, measure 0. Mu does not have any atomic support. If you just evaluate mu at a point, you get 0. And so we prove this also by looking at this kind of expression. So remember, if you look at log of di, I'll call this where di, let me define it actually. So let's write pi of t is a minimal polynomial of alpha I with integer coefficient, so it might have a leading coefficient. Then we'll let di be sort of what I call dpi, so the discriminant dpi of the polynomial pi. Then if we write log di what do we get? Well, this literally equals 2d minus 2 log of the leading coefficient of the polynomial plus a sum over all gamma conjugates that don't equal each other of log of their difference. Okay? I'm just taking log of the expression I wrote earlier with the definition of discriminant. That's what it amounts to. Okay, now di is not 0 because this is a minimal polynomial, so it doesn't have any repeated roots. And di is an integer. And log of an integer is at least log of 1, which is 0. Okay? And so this is all we're going to use the discriminant for. Because we know that whatever the expression is, it evaluates something. It's not negative. Okay? Okay, let's understand how big each term on the right-hand side is. Okay, now if you look at log of ADI, what do we know about this guy? We know this is equal to DI times the height of alpha I minus the sum over all the gamma conjugates. Right? Now we know this goes to 0. And we know that this thing average goes to 0, because that's smaller than the height. And so whatever the expression is, it sort of grows slower than d sub I. So I'm going to write this as little o of d sub I. Okay? Is everyone familiar with little o notation, big O notation? Just to remind you, sort of, F, I'll put it in the box, because we're going to be using it a lot. So F equals little o of g, where F and g are two functions, means that the appropriate limit of F over g is 0, so F grows slower than g. And F equals big O of g means that the lim sup of F over g is finite. Okay? So this means like F grows slower than any constant times g, and this means F grows at most as fast as some constant times g. Okay? Whenever these long arguments happen, it's sort of very useful to not write constants and just write little o in big O notation. All right, so the term over here is little o of d, which means this expression is little o of di squared. And if we look at log plus of sigma 1 alpha I minus sigma 2 alpha I, then by the triangle inequality, this is at most log 2 plus log plus sigma 1 alpha I plus log plus sigma 2 alpha I, which means if we sum all these guys over all pairs sigma 1, sigma 2, there's roughly d squared terms in that sum, di, just two terms, maybe times 2. And so this contributes at most to di squared times some constant. And these guys we know are little o of 1 on average, so this gives you a little o of di squared. So in other words, the sum over all these two pairs of conjugates is big O of di squared. Okay? Okay, so now if you look at the expression, this term is positive, and these terms can either be positive or negative. The positive terms are exactly captured by the sum of log pluses. So we know all the positive terms on this side sum to something which is at most a constant times di squared. So as a result, the negative terms must also sum to something which is at most a constant times di squared. Okay? So thus, if you sum all the negative terms, what are the negative terms? Well, they're exactly norm log plus one over this guy. Sigma 1 not equal to sigma 2. This is big O of di squared. This is what we need to show that mu doesn't give any point finite measure, non-zero measure. So take, I don't know, any number c in S1, in the unit circle. And take epsilon, some number bigger than 0. And now let ni be the number of sigma, number of conjugates, such that sigma alpha I minus c is less than epsilon. Okay, look at sort of the density of points which are within epsilon of this point c. So we're looking up at bunching up near a single point. So we have to show that for small enough, sort of for any, as epsilon goes to 0, the proportion of these, so this number divided by d sub I, goes to 0 as well. That's this measure clean. Okay, so because of this over here, what we get is that the sum is at least sort of ni choose 2, so let's say ni squared over 2, times number of points, this number of points over here, times log of 1 over 2 epsilon. Right? These terms are all positive. If you just look at the ones in here, you get this bump. Right? And so therefore, if you look at, because this is big O of di, what you get is that ni over di is sort of big O of the square root, I don't know, of 1 over log 1 over 2 epsilon. Sorry, am I making a mistake? No, that's right. Okay, now as epsilon goes to 0, this term also goes to 0. Okay? And that proves that the proportion of these guys, so ni over di goes to 0. So therefore, ni over di goes to 0. I goes to 0 and epsilon goes to 0, and so that means mu doesn't give any point positive measure. Questions about this? Yes.
Yeah. There was a long time ago on the other board.
On the other board.
Yeah. How do you know the sum in average goes to 0?
How do you know the sum and average of this goes to 0? Because this is bounded above by the height. This is bounded above by d times the height, right? This is exactly the Archimedean contribution of the height multiplied by d.
Each.
So what's the height, right? The height is the sum over all evaluations of this log plus thing.
Yeah. Oh yeah. Yeah. Okay. Nice.
But it's normalized a certain way, right? So you gotta. All right. So we've proven that mu doesn't give any point positive measure. Okay, but in fact this argument sort of shows a lot more. We're sort of controlling these energy integrals that we're studying over here. So, yeah, okay, so now let's make the following claim. Which is that this I of mu, which we call this log thing, which now sort of makes sense. It's not, before you have to be a little careful, because if mu assigned point C positive measure, then this would be minus infinity right away at that point. You couldn't sort of integrate this function coherently, but now you can. This guy is bigger than or equal to 0. Okay? Okay. So, what do we sort of want the proof to be? Well, we want the proof to be that what we had here with discriminant bound, we know that the sum divided by di squared goes to something which is at least 0. That's what we showed sort of before. I'll rewrite it again. But in a sense, what we're showing is that if we look at I of sort of mu sub I, then the limit of that goes to something which is bigger than or equal to 0. That's what it's sort of easy to show from that side. Unfortunately, it doesn't quite imply anything about I of mu precisely because of this outlier issue I was talking about. So more precisely, from the more fancy real analysis language, sort of Diophantine lemma, which only gives you an inequality one way, and it's all the wrong way. So whenever you're dealing with these sort of non-compact spaces or these functions with minus infinity, you have to be a little careful when you make these arguments, right? So it's not hard to go around this case, but we need to sort of deal with a potential issue. So what we do is the following. So define phi epsilon, which is the following function. It's sort of at 0 here, then at epsilon it stays 0, then at 2 epsilon it goes up to 1, and then it stays 1. Okay? I'm not going to write coordinates for it, but this is phi epsilon, it's piecewise linear function. And I'm not going to integrate I of y. What we're going to do is we're going to consider the integral of phi epsilon of this, d mu x, d mu y. Okay? So, let's do that. So, we're going to consider the integral phi epsilon of log x minus y. Sorry. No, sorry. We're going to consider, not that. We're going to consider phi epsilon of the norm of x minus y times log x minus y times d mu x d mu y. Okay? So what's the point of doing this? Well, the point of doing this is that now you've cut out the minus infinity, so all of a sudden your function is, maybe we want, and we want to do, we want to do this as well. We want to also bring it back to 0 at 1 over epsilon. Yeah, I want this not to be too big. Okay? Anyway, another point is that this function you're integrating here is bounded from below. Okay? So this is bounded from below. Okay, so now we know that if you look at I of mu I, let's call this I epsilon of mu. So if you look at I epsilon of mu I, this is the sum over all pairs of Galois conjugates sigma 1 and sigma 2. Sigma 1 not equal to sigma 2 of 1 over di squared. That's because how the measure is normalized. And now we're integrating d mu ix, d mu iy, so it's a sum over all Galois conjugates of this, of sigma 1 alpha I minus sigma 2 alpha I times log sigma 1 alpha I minus sigma 2 alpha I times, no, that's it. Okay? And so we're going to show that the limit of each of these is non-negative. So if we show I epsilon of mu I is greater than or equal to 0 in the limit. Now because these functions we're summing up are bounded from below, now we can apply Fatou's lemma, and so then by Fatou's lemma, I epsilon of mu is also at least 0. And once we have this for all epsilon, then we can take a limit and get that I epsilon, that I of mu is at least 0. So then, because these functions are increasing by monotone convergence, I of mu is at least 0. Okay? Because the phi epsilons are increasing and only in this small range where this log is negative, which means that these functions are decreasing, so if the integral of each of them is 0, so is the limit. Okay, so I'm out of time. Okay, so we'll do it next time, but basically it's not hard. We already know without the phi epsilon that this thing is non-negative. And so all we got to show is that not much happens when these guys are too close or too far. So we'll do that next time.